Today I'll be talking about 13.6 applications of the gradient. So, in the previous subtopic, we defined what a gradient was, which is, so we read this as del f of x, y is equal to the vector partial derivative of f with respect to x and partial derivative of f with respect to y. And so this gradient, this 2D vector, has a lot of applications that I'll be talking about. So the main one is that the direction of the maximum increase of this function f of x, y is given by our gradient. And then the maximum value of our directional derivative, if you also remember that from the previous subtopic, is equal to the magnitude of our gradient. And so what this means is that if we have some sort of surface, then our direction of max incline will be given by our gradient. And we can also have the direction of maximum decrease, right? Maximum decrease would just be given by the negative gradient, and then the minimum of our directional derivative would be the negative. So to prove this, we're going to first define our unit direction vector, u, which is equal to cosine theta, sine theta. And then recall that our directional derivative, for the function f of x, y in the direction of u, is equal to the dot product of our gradient and our direction vector u. So if we do this, we can use the definition of a dot product. So we have the magnitude of our gradient times the magnitude of our direction vector times cosine of phi, where phi is the angle between u and our gradient. The magnitude of u, though, is just 1 because u is a unit vector. So that means this is just the magnitude of our gradient times cosine phi. And so now, if we want the maximum value of our directional derivative, that's when cosine phi is equal to 1. And so that will mean our maximum value is going to be just the gradient. And if cosine phi is equal to 1, that means phi is equal to 0. So that means the angle between u and our gradient is 0, which indicates that our gradient is pointing in the same direction. So our gradient gives that direction of maximum increase. And then similarly, for the negative would happen, the minimum value of directional derivative happens when cosine phi is negative 1. And this is when phi is equal to pi. So pretty much a 180 degree around, and that means the opposite direction of our gradient. The exact opposite direction is the maximum decrease. And so you can picture this if you have a surface where a skier is trying to ski down a hill in a maximum decline, maximum decrease, then we can use the gradient to find that, the negative gradient. But remember that gradient is a 2D vector in the xy plane. So this is a surface. Imagine you have an xy plane underneath it. If that's the steepest decline, then this is the gradient. The gradient itself does not point up or down since it's just a 2D vector. Alright, so now let's see how this works in a problem. So let's say we have a metal plate that's a flat metal plate, so on the xy plane, and at each point we have its temperature, which is defined as T as a function of xy is equal to 20 minus 4x squared minus y squared. Okay. Then the first question is, what is the direction of the most rapid temperature increase of the greatest, or I'll say max, temp increase? Right? The direction of maximum increase, we just said earlier, is the gradient, is given by the gradient, so we can just find the gradient here. So you have del t of xy is equal to, here it will be the partial derivative of t with respect to x. So we can treat x as a variable and everything else as a constant. And so that gives us negative 8x. And the same thing with respect to y. We treat y as a variable, so this all goes to 0, and this becomes negative 2y. And then now the question is, oh, and I forgot, if we're starting from the point 2, negative 3, If we're starting from this point, then what we can do is just plug in this xy into here. So we get -16, 6. So that gives you the direction of the maximum temperature increase. Number 2 is asking for what is that rate of increase when you're going in the direction of this maximum temperature increase. And so the rate of increase is just the directional derivative because it's like the slope in that direction. And so we said that is just the magnitude of the gradient. And this is around 17.09 degrees per unit. The key thing to note is that the gradient, this gradient here, -16.6, doesn't actually give you the direction to the hottest point on the plate. Because gradient, remember, is only the maximum increase at that one point. But once you move out from that point, the gradient might change, and so your gradient might point to a different direction. Alright, so now I want to talk about a different application of gradients, which is linear regression. So let's say we have n points on the xy plane, x1, y1, x2, y2, and so on till xn, yn, right? So let's say we have the xy plane here, we have a bunch of points here. You might have seen this before, but if we want to find the line of best fit, we're trying to find a line that most accurately describes the trend of our data. And let's show how to do this with gradients. So first of all, if we just have a line y equals to mx plus b, how do we even define how good is this line at approximating these points? Well, let's just pick a point, xi, yi, and find like how good is this line just for this single point. Well, what we can do is we plug in xi into our function here, so we get y is equal to m xi plus b. So now this expression, this gives us the predicted value of y with our line, right? So this is our predicted value of y, which I will denote as y hat with this little caret. And so this is our predicted value of y, but we know our actual value of y, that's yi, right? So how good this line is we can use the error term, right, which is the difference between the line, the predicted value of y, and the actual value of y. So like, let's say this is xi, yi, then our error term is like the distance between these two. So our error is equal to y hat minus yi. Okay, and we know that y hat is this expression, so I will rewrite that here. So now that's our error term, or that pretty much tells us how good is this line for one single point. Now we want to do that for all n points, right? So we can sum that over all n points. So let's do the sum of all n points of this expression. And so this gives us a pretty good way to find how good is this line for approximating the trend in these points. But there's an issue with this. And can you see what that is? A hint is that this expression, obviously we want the error to be, the worse the line is, the bigger it is. But this error could give you, or this expression could give you negative values. And so the issue here is that this is our predicted y, right? But we don't know if our predicted y is going to be greater or less than yi, right? So let's say we choose this point over here. This expression, so this is our predicted value of y, this is the actual value of y. If we do this expression, this minus that gives you a negative value, right? And so this minus this will give you a positive value. And so these errors might cancel out with each other, which is not what we want. So how do we make this term positive always? There's two ways. One, you could do absolute value of this. One is you could do square of this. And I will do a square since the main reason being that, well, you'll see in a bit, but the derivative of like this squared is a lot easier to find than the derivative of an absolute value of x. Okay, so this expression tells us how good is this line for all n points. And so now I want to find like the average of all of this, like over all n points. So this is like the average error for all n points. So this expression is what we call the cost function in machine learning. So the cost function pretty much tells you how good is whatever your model is, right? So in this case, the cost function tells us how good our line is, right? The lower the cost function, the better our line is. And so I'll denote our cost function as C of two variables, M and B, right? And the reason for this is because our cost function, it describes a line, and a line is defined by its slope M and its y-intercept B. So those are our variables, and then x or y are just the points. Right? So now we have this cost function. So with the cost function, right, if we want the best fit line, we want to lower the cost as much as possible. So we want to find the minimum possible point on this cost function. And so the way to do that is with gradients. So let's find the gradient of our cost function. So gradients of n and b, this is the partial derivative of cost with respect to slope and with respect to our intercept. And so now how do we actually calculate these values? So first let's take the partial with respect to slope. 1 over n, that's a constant, so we can just move it outside. And if we have partial derivative of a sum, that's the same as the sum of the partial derivatives. So we can just move the sum out as well. And so now we need to find the partial derivative of this with respect to n. So we can do this chain rule on that. So first, we do 2 times this expression. And then we do partial derivative with respect to m on the inside. Right, so these are all constants, so they go to 0, and partial derivative of mxi would just be xi, so this times xi. That's our first partial derivative. The second partial derivative, very similar. We can do 1 over n, sum of I equal to 1 to n of, so partial derivative outside is 2 times that whole expression. And then times the partial derivative of the inside. So this is a constant, that's a constant, so they disappear. Partial derivative of b with respect to b is just 1. This is times 1, but I won't write that. So that's our partial derivative. And then let me simplify this. This is the same as 1 over n, and this is like the sum of 2 times, so this term is just our error term, so I'll just write error here, error times xi. This is 1 over n, sum of 2 times error. So this is our partial derivative. And so that gives the direction of the steepest descent in our cost function. But like temperature example we gave earlier, we said that this doesn't give the direction to the minimum possible point, right? This only gives at that one point. And so how do we get to the minimum possible point on the function? We use what's called gradient descent. Gradient descent is an idea in machine learning where you kind of repeat the step of finding the gradient multiple times. So like, let's say you have some sort of surface that looks like this. Right, so it's like a bowl shape, right? So let's say we start at some point here, we calculate the gradient, and we move in that direction. Get to a new point. Calculate the gradient again, move in the gradient direction, and then keep doing this over and over until you finally get to the very bottom. So that's gradient descent. Alright, so now let's do a simple bit of coding to show how this linear regression works. So let's first define some variables. We have our slope n and our y-intercept b, which we'll define to some random numbers. I'll put 0 in this case. Then we have n, which is the number of points. Let's do 8 points here. 8 points. And then we'll need a learning rate. So this learning rate, I'll go over a bit more in depth in a second what this is. And then we have our epsilon. This is kind of like our a very small number. It's going to be 1e negative 9. So this is 10 to the negative 9, and it's pretty much a constant that tells us when to stop taking gradient steps. Okay, and then we have our set of 8 points here. I've gone ahead and found and just created 8 random points. So our first point is 2.3, 3.7, and then 1.6, 2.1, and so on and so forth. And so we have 8 points here. So now what we want to do is, so first we create a, let's call this parameter step. Let's make this a random size. And so parameter step is how large how much our parameters change when it moves, right? When it updates. So our gradient gives us the direction of that change we want to go into, but it doesn't tell us how big. And so that's what the learning rate is. And so learning rate tells us how large that step is. And so pretty much while we're moving like pretty fast or pretty far, we want to continue updating. But once parameter step is less than some very small number, that means it's like not updating much anymore, we want to stop. So while it's still greater than this epsilon constant, we're going to keep updating. And so what we want to do is we want to, at each step, calculate our gradient, right? So let's define those. So we have a partial derivative with respect to slope and a partial derivative with respect to y-intercept. And to find them, we're going to loop through, right, all endpoints, right? As we loop through each point, we will add up these terms, right? So first, our error term is equal to this whole expression. So that's n, right, our slope times the x coordinate for the ith point, plus b, and then minus the y coordinate for the ith point. And so now we want to add this term to our partial derivative of slope, or of cost with respect to slope. So that means dc dn, or partial derivative of c with respect to n, we're going to add to it 2 times error times xi, so 2 times error times xi, and then we're going to divide by n. So I'll just move this over n inside since it's a constant, so divide by n. And note that here 2 and n, technically you don't really need these numbers since they're just constants. You can take them out if you want, but we will keep them here for now because just that's how the calculations work. And same thing with this, same thing with this, for this partial derivative, we're adding the same thing, but we don't have this xi term. So it's just 2 times error over n. And so this will loop over all points and then find our gradient for this cost function. Fun fact, this cost function is called the mean squared error, since it's the error squared, and we're finding the mean of it, or the average. So it's the mean squared error, and it's very common for linear regression. But now we have our gradient here, right? So now we want to update n and b, our slope and y-intercept. And so how we do that is we take n, and we're going to subtract, remember, because this is a gradient, but we want to go in the descent direction, the decline direction. So we're going to subtract, and then we're going to subtract dc dn, which is our direction in the slope direction, and then times our learning rate, right? So remember, our learning rate tells us how big that step is. So that's just a random constant. And the same thing with our y-intercept. We're going to subtract the partial derivative of cost with respect to y-intercept times our learning rate. So that updates n and b. And the last thing is to update our parameter step, right? We're going to find how big the parameter step is now. So parameter step is going to be equal to the magnitude of the change parameters. So the magnitude would be the square root of each partial derivative squared, so dcdm squared plus dcdb squared times dcdb. That gives you the magnitude of the parameter change. And remember, since we have this, we multiply by this learning rate, we'll multiply by this learning rate constant as well. And so now we have the parameter step, and that's it. And so that after doing all this, right, it should keep looping until our parameter step is small enough, and our n and b should be accurate enough. And so now let's just print out our results. All right, small typo, that should be dcdb, not dcdm. So now if we run our code, there we go, it outputs a line. And let's check if this is right. So I've gone ahead and put these points into decimals. So if we find the approximation for it, we can see that n is 0.76627 and b is 1.01724. And that is exactly what is given by our output. So there you go. That's linear regression with partial derivatives and gradients. So a couple things. I will say I did take a bit of a shortcut with this parameter step. Usually, instead of checking how big that change parameter is, you should be checking how big your changing cost function is, right? So if your cost function is decreasing very slowly at some point, then you should stop my parameter. Now usually these two are correlated with each other, so that's why I did it. But usually you would put the cost function there instead of parameter step. The last few questions I want to leave with you is looking through these variables at the top again, remind yourself what they are, and think about what would happen if you made any of these a lot larger or a lot smaller. And so that's it for our lecture on applications of the gradient.